Before asking whether the laws of physics are discovered or invented, we must slow down and ask a more basic question. What are the laws of physics, really? When we hear the word law, we often imagine something like human laws, rules written down, enforced, and obeyed. But the universe does not read books. It does not attend courtrooms. And yet, everywhere we look, nature behaves with astonishing regularity. Planets follow precise paths, light always travels at the same speed in a vacuum, atoms form predictable structures. Physicists summarize these regularities using equations. For example, Newton's law of gravitation, Maxwell's equations of electromagnetism, Einstein's field equations, Schrödinger's equation in quantum mechanics. These equations do not force nature to behave, they describe patterns we observe. At the most basic level, a law of physics is a concise mathematical description of how aspects of nature behave consistently. Already something important becomes clear. The behavior exists first. The law is written later. This simple observation will quietly shape the entire discussion. Many physicists feel, often instinctively, that laws are discovered, not invented. According to this view, the universe has an objective structure. Laws exist independently of human minds. Humans merely uncover them like explorers finding a hidden landscape. Albert Einstein strongly leaned toward this position. He believed that the most incomprehensible thing about the universe is that it is comprehensible. To Einstein, the success of mathematics in describing nature was not a coincidence. It suggested that reality itself is ordered in a deep, rational way. Under this view, gravity existed before Newton, electromagnetism existed before Maxwell, quantum behavior existed before Schrödinger. Physicists did not create these laws, they revealed them. This perspective is often associated with scientific realism and sometimes with Platonism, the idea that mathematical structures exist timelessly and objectively. There are strong reasons why many scientists favor the discovery view. 1. Universality. The same laws apply everywhere we can observe, on Earth, in distant galaxies, billions of years in the past. The hydrogen atom behaves the same way across the universe. This strongly suggests the laws are not human-made conventions. 2. Predictive power. Physics does not merely describe what we already see, it predicts what we have never observed. Dirac predicted antimatter using equations. Einstein predicted gravitational waves a century before detection. Quantum electrodynamics predicts experimental results accurate to 12 decimal places. It's hard to believe that something invented by humans could work with such precision. 3. Constraint on imagination. Physicists often discover that nature refuses to follow beautiful ideas unless they are correct. The universe does not care about elegance or preference. It behaves the way it behaves. This resistance gives the impression that laws are found, not chosen. Not all physicists and philosophers agree that laws of physics exist out there independently of us. According to the invention view, laws of physics are human-created models, mathematical tools designed to summarize observations, useful approximations, not ultimate truths. In this perspective, laws do not obey nature. Nature simply behaves, and we describe that behavior. The philosopher and physicist Pierre Duhem argued that physical theories are not explanations of reality itself, but economic representations of experimental laws. From this view, laws are maps, not the territory. Different maps can describe the same landscape. No single equation captures reality completely. The invention view has powerful arguments behind it. 1. Multiple theories, same phenomena. Throughout history, very different theories explained the same observations. Newtonian gravity turned into Einstein's general relativity. Classical mechanics turned into quantum mechanics. Thermodynamics turned into statistical mechanics. Each theory worked well in its domain, yet later turned out to be incomplete. If laws were truly fundamental objects, why would they change? 2. Idealizations everywhere. Physics relies heavily on simplifications. Point particles, frictionless surfaces, perfect vacuums, continuous fields. These things do not exist exactly in nature. They are inventions that make calculation possible. 3. Underdetermination. Often, multiple mathematical models fit the same data equally well. This suggests that data alone does not uniquely determine the law. Human choice, aesthetics, and convenience play a role. At the heart of this debate lies a deeper question. Is mathematics itself discovered or invented? Physics is written in mathematics, so the status of physical laws depends heavily on the status of math. If mathematics is discovered, laws may be discovered too. If mathematics is invented, laws may be inventions layered on observations. Physicist Eugene Wigner famously called this the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract symbols created by the human mind describe the universe so perfectly? No consensus exists. Some argue mathematics reflects deep structures of reality. Others argue it reflects how human brains evolved to recognize patterns. This unresolved tension mirrors the laws of physics debate itself. Here is something rarely said clearly. Most working physicists do not constantly worry about whether laws are discovered or invented. In practice, they build models, test predictions, refine equations, discard what fails. Richard Feynman was very honest about this. He once said, in essence, physics is about finding rules that describe nature's behavior, not explaining why those rules exist. This reveals an important shift. Philosophers ask what laws are. Physicists ask what laws do. In daily research, laws function as tools, powerful, predictive, and provisional. This pragmatic attitude quietly supports the invention view, even among physicists who emotionally lean toward discovery. The debate becomes sharper when we look at quantum mechanics. Einstein's view. Einstein believed laws reflect an objective underlying reality. Quantum randomness was incomplete knowledge, not true chance. His famous objection, God does not play dice. For Einstein, laws must exist independently and deterministically, even if hidden. Bohr strongly disagreed. Bohr argued that physics does not describe reality as it is, it describes what we can say about nature. In quantum mechanics, measurement matters. Observation affects outcomes. Laws describe probabilities, not certainties. Bohr's view suggests laws are context-dependent, observer-related, conceptual frameworks, not mirrors of reality. This disagreement was not philosophical fluff, it shaped modern physics. Modern physics has undergone a subtle but profound shift. Instead of asking, what are the laws, physicists now often ask, what are the symmetries? A symmetry means something stays the same when something else changes. Examples are space looks the same everywhere, conservation of momentum, time behaves uniformly, conservation of energy. This connection was proven by Emmy Noether in 1918. Every continuous symmetry corresponds to a conservation law. This result is one of the deepest discoveries in physics. Here's the striking implication. Laws may not be fundamental. Symmetries may be deeper than laws. Laws could be consequences of symmetry, not the foundation. This idea strongly reshakes the debate. One of the most important modern insights in physics is this. The laws we use depend on the scale at which we look. At everyday scales, Newton's laws work extremely well. At atomic scales, quantum mechanics is required. At cosmic scales, general relativity dominates. This led physicists to a powerful idea, effective laws. An effective law is not fundamentally wrong, it's accurate within a limited domain. For example, the gas laws work without tracking individual molecules. Thermodynamics works without knowing quantum mechanics. Biology works without solving Schrödinger's equation. This suggests something profound. Laws may emerge rather than exist fully formed at the deepest level. Physicist Steven Weinberg emphasized that higher-level laws are not illusions. They are real, but not fundamental. This weakens the idea of eternal, fixed laws and strengthens the idea that laws are context-dependent descriptions. In quantum field theory, physicists discovered a strange problem. When calculating interactions at very small scales, equations often give infinities. Results become meaningless. To fix this, physicists developed renormalization. Renormalization shows that what we call constants depend on energy scale. The laws we write change as we zoom in or out. Physicist Kenneth Wilson showed that physics at one scale can be largely independent of physics at much smaller scales. This means there may be no single final equation visible from our scale. Laws are layered, not absolute. This is a major blow to the traditional naive discovery view of laws as timeless, unchanging objects. Perhaps the deepest modern challenge to traditional laws comes from emergence. Emergent phenomena are not obvious from fundamental equations, arise from collective behavior. Examples: temperature emerges from molecular motion. Consciousness emerges from neurons. Fluid turbulence emerges from simple equations. The equations governing individual particles do not contain heat, pressure, or meaning, and yet these things undeniably exist. Physicist Philip Anderson famously wrote, "More is different." This suggests that laws at higher levels are not reducible in any simple way to lower-level laws. If true, then laws are neither purely discovered nor purely invented, but patterns that crystallize at different levels of complexity. Modern theoretical physics increasingly asks a radical question: what if laws themselves are not fundamental? This idea sounds extreme, but it is taken seriously by leading physicists. The motivation comes from a problem. Laws describe regularities, but laws themselves do not explain why those regularities exist. Physicist Lee Smolin has argued that treating laws as timeless may be a mistake inherited from classical thinking. In some modern approaches, laws may evolve, laws may be approximate, laws may be emergent features of deeper principles. This shifts the focus from laws to structures, constraints, or processes. Importantly, this is not philosophy alone. It is driven by failures to unify general relativity, quantum mechanics. One of the most serious modern ideas is that information, not laws, may be fundamental. This idea appears independently in multiple areas of physics. Black hole physics. Jacob Bekenstein and Stephen Hawking showed that black holes have entropy. Entropy scales with surface area, not volume. This led to the holographic principle, later developed by Gerard 't Hooft and Leonard Susskind. The implication: physical reality may be encoded in information, not fields or particles. Quantum mechanics. Quantum states fundamentally encode probabilities and information about possible outcomes. John Wheeler summarized this with the phrase, "it from bit," meaning physical things, it, arise from information, bit. If this is correct, then laws may be rules for information processing, not fundamental commands of reality. Another advanced idea, taken seriously but cautiously, is that the universe behaves like a computation. This does not mean the universe is literally a computer built by something. It means that physical evolution may follow computational rules. Physicists involved in this line of thought include Seth Lloyd, David Deutsch. Evidence comes from limits on information storage, Bekenstein-bound, limits on computation speed, Margolis-Levitin theorem, and discrete quantum processes. In this view, laws resemble algorithms. Reality unfolds step by step. But here's the critical point: algorithms can be implemented in many ways. This suggests laws may be discovered patterns in how information evolves, not absolute objects existing outside reality. This view occupies a middle ground between invention and discovery. References: E. Noether, 1918, Invariant Variation Problems. E. Wigner, The Unreasonable Effectiveness of Mathematics. S. Weinberg, Dreams of a Final Theory. For much of the 20th century, many physicists believed in the possibility of a final theory, a single, complete set of equations describing all physical reality. Physicist Steven Weinberg was one of its strongest advocates. He argued that physics shows a historical trend from many separate rules toward fewer, deeper principles. Examples: electricity and magnetism unified by Maxwell, space and time unified by Einstein, weak and electromagnetic forces unified in the Standard Model. This suggests convergence. However, modern physics has raised serious doubts. Reasons for skepticism: quantum gravity remains unresolved. Multiple consistent mathematical frameworks exist.
Emergence suggests no single level controls all others. Physicist Nancy Cartwright famously argued, "The laws of physics lie." By this, she did not mean physics is wrong, but that laws are idealized, context-dependent tools, not universal dictators. If Cartwright is correct, then a final theory may describe some level, but not the total richness of reality. This challenges the very idea that laws are ultimate objects waiting to be discovered. One of the most mysterious facts in physics is simplicity. The universe can be described by a small number of equations with remarkable mathematical elegance. Paul Dirac believed that fundamental laws must be mathematically beautiful. Yet nothing logically requires reality to be simple. The universe could have been chaotic, irregular, or incompressible. Several serious explanations have been proposed. 1. Selection effects. We only exist in universes where regularities are stable, complexity can arise. This is related to the anthropic principle, widely discussed by Brandon Carter and others. 2. Compression argument. Some physicists suggest laws are the shortest possible descriptions of observed patterns. Simplicity reflects information compression, not metaphysical truth. And 3. Deep mathematical structure. Others argue that reality is mathematical at its core. Simplicity reflects an underlying logical necessity. None of these explanations is settled, but the question itself strongly suggests that laws may be descriptions of deep order, not commands imposed on reality. After going this deep, many physicists reach a surprising conclusion. The question may be wrongly framed. Why? Because it assumes laws are things that must be either out there or in our minds. But laws may be better understood as stable relationships between observable quantities, expressed using human-created mathematics. In this view, the patterns are discovered, the language is invented, the formulation is negotiated between mind and world. Physicist Heisenberg suggested something close to this when he said, "What we observe is not nature itself, but nature exposed to our method of questioning." This dissolves the sharp divide, not purely discovered, not purely invented, but co-created through interaction between reality and human cognition. References: Steven Weinberg, Dreams of a Final Theory; Nancy Cartwright, How the Laws of Physics Lie; Paul Dirac, The Principles of Quantum Mechanics.
One unavoidable question emerges once we question the fundamentality of laws. Are the laws of physics unique? Or could there be many sets of laws? This question arises not from philosophy, but from modern theoretical physics itself. In models of cosmic inflation developed by Alan Guth and others, different regions of space-time may undergo different symmetry breakings. This can lead to different effective laws in different regions. In string theory, there are an enormous number of mathematically consistent solutions. Each solution corresponds to different constants, particles, and forces. Estimates suggest numbers as large as 10 to the 500 possible vacuum states. This does not mean all are real, but it shows that physics itself allows many internally consistent law sets. If this picture is correct, laws are not unique. Laws may be environmental, like phases of matter. This deeply challenges the idea that laws are timeless necessities. Physicist Max Tegmark proposed a bold idea. Physical reality is a mathematical structure. This is not widely accepted, but it is seriously discussed. In this view, there is no separation between equations and reality. The universe does not obey laws, it is the laws. Implications? Discovery versus invention collapses. Mathematics is not a language describing reality. Mathematics is reality. Criticism from physicists includes lack of testable predictions, confusing description with ontology, explaining too much by explaining nothing.
Still, the idea is important because it represents the strongest possible discovery view. Even critics agree it forces us to confront why mathematics works at all. At the deepest level, some physicists argue that laws are secondary to something even more basic. Why does reality admit stable relationships that can be written as equations? Equations assume repeatability, identity, stability across time, but none of these are logically necessary. Philosopher-physicist Voss von Freusen suggests science does not reveal ultimate truth, it reveals empirically adequate structures. From this view, equations work because the universe has persistent regularities, but those regularities may have no deeper explanation. Physicist John Wheeler framed this starkly. Why does the universe exist? Because it is self-consistent. This hints at a possible endpoint where laws explain behavior, but nothing explains why laws exist. At that point, physics meets its conceptual horizon. References: Alan Guth, Inflationary Cosmology; Leonard Susskind, The Cosmic Landscape; Max Tegmark, Mathematical Universe Hypothesis. There's a quiet fact underlying all of physics, rarely stated clearly. Reality is intelligible. Experiments done today agree with equations written decades ago. Observations made on Earth match observations made across billions of light years. This intelligibility is not required by logic. A universe could exist that is irregular, inconsistent, locally unpredictable, and yet ours is not. Physicist Albert Einstein openly admitted his astonishment. The eternal mystery of the world is its comprehensibility. This is not a poetic remark, it is empirical. Physics works because reality has stable patterns. But here's the crucial point. Physics explains how patterns behave. Physics does not explain why patterns exist at all. This places intelligibility itself outside physical law. A modern reinterpretation increasingly adopted by physicists is this: laws are constraints on what can happen, not instructions telling nature what to do. For example, conservation of energy does not cause motion, it restricts which motions are possible. This idea appears strongly in Hamiltonian mechanics, variational principles, least action formulations. In fact, many laws of physics can be derived from a single principle. Nature follows paths that extremize action. This suggests laws are not mechanisms, they are boundary conditions on possibility. Physicist Julian Barber emphasizes that laws do not operate in time, they describe timeless relationships. If true, then laws are not entities inside the universe, but structural features of possibility itself. This reframes the discovery versus invention debate entirely. Classical physics assumes laws are timeless, but modern cosmology challenges this assumption. At the beginning of the universe, temperatures were extreme, symmetries were unbroken, familiar particles did not exist. As the universe cooled, symmetries broke, forces separated, new effective laws appeared. This means the laws we observe today did not always exist in this form. Physicist Lee Smolin argues that laws may have a history, just like the universe does. In this view, early universe, fewer distinguishable laws. Later universe, richer, more specific laws. If laws evolve, they cannot be eternal objects. They are features of cosmic development. This idea is speculative, but grounded in real cosmological models. References: Albert Einstein, Physics and Reality; Julian Barber, The End of Time; Lee Smolin, The Life of the Cosmos; Hamiltonian and Lagrangian Mechanics. An uncomfortable but unavoidable question now arises. To what extent do the laws of physics reflect the structure of reality, and to what extent do they reflect the structure of the human mind? This is not speculation. It is studied seriously in Cognitive Science, Philosophy of Science, Foundations of Physics, Human Brains Evolved to Detect Patterns, Compress Information, and Predict Outcomes Efficiently. Physicist and philosopher Hermann von Helmholtz argued that scientific laws are inferences drawn from experience, shaped by how humans process information.
This does not mean laws are arbitrary. It means reality provides regularities. The human mind selects certain representations of those regularities. For example, we favor smooth equations over irregular ones. We prefer symmetry and simplicity. We discard descriptions that are too complex to use. Thus, laws may sit at the intersection of external structure and cognitive constraints. This helps explain why laws feel both discovered and constructed. Not all mathematics appears in physics. Nature seems to prefer differential equations, group theory, linear operators, geometry, and topology. Why these and not others? Physicist Eugene Wigner's puzzle returns here, but modern insights refine it. Several explanations are actively studied. 1. Stability. Structures used in physics tend to be robust under small changes, insensitive to noise. Unstable mathematical structures do not survive contact with reality. 2. Universality. In complex systems, very different microscopic details lead to the same macroscopic behavior. This is why fluids obey the same equations. Phase transitions share universal features. Renormalization theory explains why certain mathematics keeps reappearing, independent of underlying details. 3. Compressibility. Mathematics used in physics often provides the shortest description of regular behavior. This suggests laws may be optimal compressions of reality, not ontological primitives. At this depth, many philosophers of physics argue something subtle. The word law may be a metaphor we cannot escape. Nature does not legislate. Particles do not obey. Fields do not choose. Yet we keep using legal language, laws, violations, constraints, symmetries. Why? Because human understanding is narrative-based. We explain behavior using rule-like concepts. Prediction requires stable expectations. Philosopher Ludwig Wittgenstein warned that many philosophical problems arise from language misleading us. Applied to physics, law may not name a thing. It may name a role in explanation. In that sense, laws are real as explanatory structures, but not necessarily real as objects. This reframes the entire debate without denying physics its power.
At this depth, some physicists and philosophers ask a radical but serious question. Is it even coherent to imagine a universe without laws? This is not a thought experiment for fun. It tests what laws actually are. If a universe had no stable regularities, no repeatable behavior, no persistence of identity, then measurement would be impossible, memory would be impossible, prediction would be impossible. In such a universe, physics itself could not exist. This leads to an important conclusion. The existence of laws may not be a separate feature of reality. It may be identical to the existence of stable reality itself. Physicist David Deutsch argues that explanatory power is a fundamental feature of reality. Universes that do not admit explanations are physically meaningless. Thus, asking why there are laws may be like asking, why is reality consistent enough to exist? At this level, laws stop looking like optional additions and start looking like conditions for intelligible existence. One of the most remarkable empirical facts about our universe is this: we can predict the future. This sounds obvious, but it is not. Prediction requires stability of patterns, persistence of identity through time, and independence from distant unknown factors. Yet quantum mechanics shows fundamental randomness, probabilistic outcomes, and chaos theory shows extreme sensitivity to initial conditions. Despite this, prediction still works, within limits. Physicist Ilya Prigogine emphasized that nature balances order and instability. Too much order, nothing new happens. Too much chaos, nothing predictable happens. Our universe exists in a narrow middle region, enough regularity for laws, enough openness for novelty. This suggests laws are not rigid scripts, but statistical scaffolding, enabling prediction without eliminating uncertainty. As physics advances, it repeatedly encounters a boundary. Explanations eventually terminate.
For example, why these constants? Deeper theory. Why that deeper theory? Symmetry. Why that symmetry? Mathematical consistency. Why consistency at all? No further answer. Physicist Steven Weinberg admitted that at some point, explanations run out, not because we are ignorant, but because there is nothing left to explain. This does not mean science has failed. It means science has reached its conceptual horizon. Beyond that horizon, questions remain meaningful, but answers may not be physical. At this boundary, the question, are the laws of physics discovered or invented, transforms into something deeper. What does it mean for anything to be explainable at all? Physics can approach this boundary, but it cannot cross it without ceasing to be physics.
References: David Deutsch, The Beginning of Infinity. Ilya Prigogine, Order Out of Chaos. Steven Weinberg, Limits of Scientific Explanation. At extreme depth, physicists begin to distinguish between two very different ideas. Necessity. Laws must be this way. No alternatives are possible. Inevitability. Given something exists, laws arise automatically. This distinction matters enormously. Some researchers argue that laws are not logically necessary, but once any stable reality exists, laws become unavoidable. Why? Because without stable identities, repeatable relations, consistent transitions, there is no persistence, and therefore no universe. Physicist John Archibald Wheeler hinted at this when he suggested reality may be self-excited. Law-like behavior emerges simply because consistency is required for existence. In this view, laws are not imposed. Laws are the minimum structure required for anything to persist. This reframes the question entirely. Laws may not explain reality. Reality may explain laws. We often ask why mathematics works, but a sharper question is, why does any symbolic structure work at all? Physics assumes identity, A equals A, transitivity, continuity or discreteness, logical consistency. These are pre-mathematical assumptions. Physicist Kurt Gödel showed that no formal system can explain its own consistency. Consistency must be assumed from outside the system. Applied to physics, laws presuppose logic. Logic presupposes consistency. Consistency cannot be explained by laws. This suggests that mathematics does not ground reality. Consistency grounds both mathematics and reality. At this level, laws appear as expressions of consistency, not fundamental entities. A final deep distinction used in advanced foundations. Law-governed. Laws exist first, the universe follows them. Law-generated. The universe's behavior gives rise to laws. Most modern approaches quietly favor the second. Why? Because early universe physics suggests changing effective laws. Quantum gravity models lack fixed background laws. Emergence shows higher-level laws appear from lower-level interactions. Physicist Carlo Rovelli argues that physics describes relations, not objects, and laws summarize stable relations. In relational views, there are no absolute laws, only persistent relational patterns. Laws, then, are discovered as patterns, invented as descriptions, stabilized by consistency and symmetry. They are neither illusions nor dictators. They are crystallized regularities. References: John Archibald Wheeler, Self-Excited Universe, Kurt Gödel, Incompleteness Theorems. At the deepest level reached so far, we arrived at this idea. Laws arise from consistency rather than command. But this immediately raises a final, unavoidable question. Why is reality consistent at all? Physics itself cannot answer this in the usual sense because every physical explanation already assumes consistency. Experiments assume repeatability. Equations assume logical structure. Consistency is not explained by laws. It is presupposed by physics. Physicist Hermann Weyl recognized this boundary clearly when he wrote that the laws of nature presuppose a harmony between experience and reason. This suggests that consistency is not a physical fact among others. It is the background condition that makes facts possible.
At this depth, physics does not fail. It simply reaches the point where explanation can no longer go further without changing its nature. Now, with all layers visible, the original question can be re-examined honestly. Are the laws of physics discovered or invented? At shallow levels, the debate looks binary. At deep levels, the binary dissolves. What physics actually shows is this: regularities in nature are discovered. Mathematical descriptions are invented. Law-like structures emerge from stable relations. Formulations are shaped by human cognition. Physicist Werner Heisenberg captured this balance precisely. Natural laws are not simply discovered facts nor arbitrary inventions. They are expressions of the interaction between humanity and nature. So the answer is not discovered or invented, but rather discovered through invention. This is not a compromise, it is a deeper resolution. One might ask, why does this question refuse to go away even after centuries of progress? Because every major advance in physics reopens it. Newton, are laws absolute? Einstein, are laws frame-dependent? Quantum mechanics, are laws probabilistic? Cosmology, did laws change over time? Quantum gravity, are laws even fundamental? Each time physics deepens, the status of laws becomes less solid, not more. This tells us something important. The question is not a flaw in physics, it is a signal that physics is approaching its conceptual edge. At that edge, physics does not collapse into speculation. It becomes quiet, careful, and honest about its limits. So are the laws of physics discovered or invented? After going all the way down, the most accurate statement physics allows is this: the universe exhibits stable, intelligible regularities. Humans discover those regularities through observation. We invent mathematical languages to describe them. What we call laws are compressed expressions of deep consistency. The laws are not commandments written into reality, nor are they mere human fictions. They are the meeting point between a structured universe and a structured mind. And perhaps that is why the question itself feels so profound, because in asking it, the universe is, in a sense, trying to understand itself through us.